Lesson 9-3 is all about, as the title implies, properties of logarithms. Um, in 9-1, we spoke a lot about what exponential relationships were, and by the time we got to 9-2 and discovered the logarithm, it came to our attention that logarithms and exponents are inverse functions of one another. So we've studied the properties of exponents. It follows that we would want to study the properties of logarithms. The good news is that there's really no new properties to learn here. The properties are very much the same as they were for exponents. So let's see if we can make that a little bit more explicit here. Here I'm asking you to consider a few exponent operations, and my goal is to connect to the theme of exponent properties to logarithmic properties in 9-3. So let's take a kind of a quick look and a close look at these. Uh, it should not come as any surprise that if you multiply 5 to the fourth power times 5 to the ninth power, because the bases are the same, you now have free range in order to add those exponents, and so you get 5 to the 13th. Just as a reminder, no one is arguing that you need to commit this to memory. I think it's quite logical that if you have 4 5s and 9 5s, and you intend to multiply them all as a big chain, you're going to end up with 13 of these 5s. So let's stay grounded in this idea of being reasonable and thinking through what it is we're doing. So it turns out when you multiply exponents, you're adding those powers. Here we have x to the 17th divided by x to the 6th. In point of fact, that really means we should be, because the bases are the same, subtracting those powers and ending up with x to the 11th. And finally, a reminder that if you have exponentiation, which is a fancy way of saying a power raised to a power, then what you're actually doing with these powers is multiplying them. So that x to the ninth raised to the third power is in fact x to the 27th. So what's there for us to notice? Well, let's notice that in all of these problems the bases were the same. Let's also notice that the operation of multiplication led to addition, division led to subtraction, and exponentiation here led to multiplication. These are the properties that we're trying to elucidate here. And so you shouldn't find it too surprising that when it comes to logarithms, the same exact properties exist. So I won't read through all of them, but for instance, log base b of some product, m times n, is the same as asking for log base b of m plus log base b of n. That sounds like some pretty sophisticated jargon, but in fact what it's saying is if I'm asked to find the logarithm, the power of some base that produces this product, that's the same as finding those powers individually and then simply adding them. So for each of these properties, exponent properties is kind of an analog over here, where this is the product property. Here's its corollary. Here's the division property, and here's its buddy over here. And then here's the exponentiation property. And oh, sorry, the exponentiation property connects here, and the quotient property connects here. So how can we put this into practice? Well, there's some obvious connections. Uh, for instance, if we're asked to find log base 3 of 9 times 81 without a calculator, your first inclination might be to multiply 9 and 81. But why do that? Why give yourself a larger number, more complex number to deal with, when in fact you can think of this problem as what? As, well, log base 3 of 9 times 81 is the same as log base 3 of just 9, and whatever that power is, because this is a multiplication problem, I'd be adding that on to log base 3 of 81. So you should have some familiarity with powers of 3. The power of 3 that gives you 9 is 2. The power of 3 that gives you 81 is 4. The sum of 2 and 4 is 6. Notice that this multiplication problem turned into an addition problem, and that's the logarithmic property we're trying to make clear here. Of course, in mathematics, there's different ways to think of things, and I want to offer you a different perspective. You could have written these two factors as 3 raised to some power. So log base 3 of 3 squared times log base 3 of 3 to the 4th is the same as log base 3 of 3 to the 2 plus 4. And this here is really a key part of the problem, because think about what you're really asking. What power of 3 will produce 3 to the 6th power? And the answer is self-evident. The power of 3 that will give you 3 to the 6th is the number 6. So there's some obvious logarithmic connections and applications of properties. What about things that are perhaps not so obvious? Let's have a look at those and give ourselves kind of a chance to extend. So this is a pretty weird problem to begin with, and this comes from the textbook. I didn't come up with this on my own, but I love the value of this. You're asked to use what appears to be this kind of random bit of information. You're told that the log base 2 of 3 is approximately equal to this decimal here, meaning that if you raised 2 to this power, you'd end up with something really close to 3. And then you're asked to take that clue, that information, and try to approximate the value of log base 2 of 48. Um, so, how am I supposed to take this apparently random bit of information and approximate this value? Well, first, let me tell you that this is something that students across the world had to do for years. Before the advent or the ubiquity of calculators, students were given log tables. So you were given uh, in a textbook or on sheets of paper, hundreds and hundreds of logarithms. And based on those logarithms, you'd have to go find out logarithms of other numerical values. So this problem is kind of steeped in historical tradition. Of course, now with the calculator, we could just ask this, but can we use log properties to figure out what log base 2 of 48 is? And so here's what I've done. I've recognized that I can think of 48 differently. One way to think of it is as the product of 3 and 16. Now, you might wonder, why have I chosen 3 and 16? Because I know log base 2 of 3 is approximately equal to this decimal, so this expression has a known value. And log base 2 of 16 is really convenient because I know that the power of 2 that produces 16 is 4. So by being kind of clever here, I can take simply the number 4, add it to this decimal approximation, and end up with a pretty good answer here of 5.5820. Now, what does this number mean? This means that if you take 2 as a base and raise it to this power, you should get an answer pretty darn close to 48. And so let's just give that a test run. If we take 2 and we raise it to the 5.58 2 power, you'll notice that here this answer, this of 47.9, is awfully, awfully close to 48. We didn't expect an exact answer because we started out by using an approximation rounded to the 4th decimal place. So given the tools that we had at our disposal, we did really well. Let's try that again. Let's see how else we can do some clever thinking here using these log properties. So given that log base 5 of 2 is approximately equal to this decimal here, our job is to approximate the value of log base 5 of 250. And I haven't the faintest idea what power of 5 produces 250, but again, by kind of thinking of factors of 250, you can come up with 2 and 125. Remember that log base 5 of 2 is known, and you should also know that the power of 5 that produces 125 is just a number 3. So once more we've used, and we've been using the same logarithmic property, the product property. Once more we figured out that, well, the power of 5 that produces something really close to 250 is 3.4307. Um, let's change that dynamic a little bit. Let's see if we can use other properties and kind of dig a little bit deeper. So this time I'm given 2 clues. I'm given log base 3 of 5, and I'm given log base 3 of 20. And somehow, some way, I have to combine these 2 bits of information on my own without a calculator to come up with log base 3 of 4. So where's the connection there? Really, the thinking here is, how can I use the numbers 5 and 20 to connect to the number 4? So you may have guessed it, I'm going to use the quotient property and rewrite log base 3 of 4 as log base 3 of 20 divided by 5, which is just another name for 4. These two are more useful to me because I know approximately what log base 3 of 20 and log base 3 of 5 are. So given that this is ostensibly a division problem, really the quotient property says once you know these individual logarithms, you should be subtracting them. So you should not find it Particularly surprising when in my next line, I'm going to be finding the difference between this decimal approximation and this decimal approximation. And again, now I can tell you that the power of 3 that produces 4 is this decimal here. Um, let's have a look at one more that kind of falls into this category. And in doing so, try to use one more logarithmic property. This time I'm just given one clue. Log base 3 of 7 is this decimal. And I'm asked for log base 3 of 49. It's so important not to just kind of get dragged into falling into an algorithm. Let's just think about this for a minute. 3 to the first power is 3, 3 to the second is 9, 3 to the third is 27, 3 to the fourth is 81. So whatever answer I get here, it should fall somewhere between 3 and 4. And that's a pretty good rough estimate. But as you do these problems, you should also kind of allow yourself an opportunity to do some of that same just mental math to get a sense of where the answer lies. So there's two ways I thought of this problem. Here's one where I thought of the number 49 as the product of 7 and 7. When I do it this way, I end up taking this value and simply adding it to itself because the product property dictates you do so. Here I thought of it differently. I thought of the number 49 as 7 squared, and using the exponentiation or power property, think of what's happening here. You're asking what power of 3 produces 7, and then you're taking that answer and raising it to another power. So when you have the power of a power, you're multiplying those powers, which is what we did with exponents. So if I multiply 2 and 1.7712, again I get 3.5424. That's the power of 3 that's going to give me something really close to 49. And as I predicted, the answer was between 3 and 4. Finally, let's have a look at um, logarithmic equations and see how we can use log properties to kind of sort those out and make sense of those. So originally I'm asked to solve this equation here. And the first thing I notice is that the bases are the same on the left-hand side, and it appears to be an addition problem. And so if it appears to be an addition problem, that means that what was happening originally at the outset was that this value, since it's being added to this value, and both of these are powers, this was originally a multiplication problem. So what's really happening is that x is being multiplied by x times, or x minus 6, excuse me. And then you might be initially surprised that here I've written 4 squared. You shouldn't be. Remember that if you look at the left side of the expression or equation, the question is what power of 4 will produce these answers here? And albeit, or we will be multiplying them, but the answer to this question is the number 2. So this isn't really just the number 2. This is a base of 4 being raised to the second power. And from this point forward, this just becomes an algebra problem. It actually turns into a beautiful little quadratic. And if you factor out, you will find that there appear to be two different answers of -2 and 8. But having studied the graphs of logarithmic functions, we are cautious about the domain. Imagine if you plugged in a -2 here, you'd have -2 minus 6, which is -8. You cannot take a base of 4, raise it to any power, and get an outcome of -8. So you're going to go ahead and dump that -2. It does not work. Only 8 works. And that takes us to our last logarithmic equation, which is here, and you're seeing it in its entirety. I actually found myself applying two different logarithmic properties. One was, since I'm multiplying 3 times a power, that comes from an exponentiation problem. We're kind of working in reverse here. So log base 5 of x is being raised to the third power. So from the first to the second line, I've only made that one change. From the second to the third line, I'm recognizing that this subtraction sign here indicates that this was originally log base 5 of x to the third divided by 4. And finally, once I see that the bases are the same, I don't even need to acknowledge those bases. I simply write that x cubed over 4 is equal to 16. And finding the cube root of both sides reveals that x is 4. For those of you that are interested in a little bit of history and kind of this reminder that mathematics is kind of the culmination of tens of thousands of different people's contributions over the course of history, logarithms are frequently given, or the credit for developing logarithms are frequently given to this guy, John Napier. He was a Scottish mathematician and had other occupations as well. And he was around in the in early 1600s. And he is credited with actually pushing science and mathematics forward really by decades. Because if you think about what logarithms are doing, they're effectively taking, for instance, multiplication problems and turning them into addition problems. So imagine if you can take really complicated operations and go from multiplying to massive numbers. Let's say you're an astronomer back in the 1600s, and now you get to add those numbers if you convert them to their logarithms. He is really kind of a big part of the promotion of math and science. The other thing that's interesting about him is that he was, I think we're making a mistake of thinking of him as like a modern day mathematician, but he was quite quirky. Some of the things, and this is just the Wikipedia page. You can imagine if you delve deeper, you'll find other stuff. Not only is he given credit for his contributions to math, but he also dabbled in theology and the study of religion and different scriptures. He had some pretty strong views at that time. He developed, as it says here, a strong anti-papal reading, going so far as to say that the Pope was the Antichrist, and that's pretty incendiary stuff. Not only was he a mathematician, but he tried to use mathematics to predict the date of the apocalypse. So, not ordinary fare for what we would consider to be a person just dabbling in numbers. And as luck would have it, he also had an interest in the occult, specifically in things like necromancy, which is kind of the mysticism and dark arts of the dead and trying to resurrect the dead. So, why do I share this with you? Because frequently we think of math as just as this kind of stuff. It's just numbers on a page and operations. But one of the things I've tried to promote to you this year is that there's this real beauty and history and story and narrative behind mathematics. And I think the more of it you know, the more you connect with the subject. It gives it a more humane feel. Hope you found that helpful and wishing you luck with the problems that are to come.